G'day Method students. In this video we're going to go through a few exam questions. These are in our notes straight after exercise 13b. And I guess these exam questions in one sense you could consider to be year 11 probability questions. However, they're all, got a pretty high degree of difficulty and they're all quite common types of exam questions as well. So it's probably good to go through and see some strategies that you can apply because these are the sorts of questions that do come up pretty regularly on exams. Okay, let's get into it. There's 4 questions to go through. So the first one is a multiple choice question, which means we're allowed to use our calculator. And it says a bag contains 4 white balls and 6 black balls. 3 balls are drawn from the bag without replacement. So that means that after you take one out, you don't put it back in and then choose another one. You keep it out and then pick the next one. The probability that they are all black is. Now, one of the things that you've got to decide when you read a question like this is what formula or diagram is going to be helpful here. And this has got that sense of one thing occurring after another, which means we can think of this as a tree diagram question. Now, if you're pretty familiar with tree diagrams, you often don't have to draw them in order to answer the question. You can just picture them and know what's going to be happening. But at least to get things started, let's say we were going to draw the tree diagram. So we've really either got white or black as the 2 outcomes each time we draw a ball. And remember that we're choosing 3. So white, black, black, and then obviously that can happen one more time. Right, now the event that we're interested in is that the probability that they are all black. So we want black, then black, then black, right? So the part of the tree diagram we can focus on is this part here. Now, 4 white and 6 black means there's 10 in total. So when we choose that first one, we've got a 6 in 10 chance of choosing a black ball, right? But because this is happening without replacement, when we go to choose the next ball, instead of having 10 left in the bag, there's only 9. And if the first ball we chose was a black one, then what's left in here is there's only 5 black left in the bag, right? So it's 5 out of 9, there's 5 black balls out of 9 when we make that second choice. And if we pick a black ball on the second choice, then left in the bag is going to be 4 black balls out of 8 in total, right? So we didn't need to fill all the other information in. We can just say that the probability of getting black, then black, then black is equal to 6/10 times 5/9 times 4/8. Now you can go ahead and simplify that if you want to, but I'd be just chucking that into the calculator as is, and we'll get our answer. So we've got 6/10 times shift divide, by the way. So pushing shift then divide gives you the fraction template. That can be a little small time saver. So you go shift divide and that brings up the fraction template. Oops, missed the time symbol there. Now the options were all in fractions, so I'm going to have the calculator in standard mode and we get 1/6. So that's option A. Okay, so a good tree diagram question there, and that key being without replacement, so the probabilities we're changing at each selection. Okay, question 6. 2 events A and B from a given event space are such that the probability of A is equal to 1/5 and the probability of B is equal to 1/3. Question's got 2 parts here, and it goes on to talk about, probability of A dash intersection B and A intersection B. With these sorts of questions, as soon as you get questions about probabilities of A and B and then intersections and that sort of thing, my inclination would be that it's probably either going to be a Venn diagram or probability table question, and often you can just use whichever one you prefer. For a question like this, I would suggest a probability table, partly because the probability table's got those totals on the outside that a Venn diagram doesn't have. Okay, so what I mean by this is we can say, well, let's set up our table and we'll make it, this can be A, this can be A dash. Then we've got B and B dash. All right, and we know that with this probability table, we're going to have our row and column on the outside that gives us the totals and that the sum of the probabilities is going to equal 1. Now, if we put in what we know that the overall probability of event A was 1/5. the overall probability of event B was 1/3, Okay, now the question's saying if the probability of A and B is 1/8, calculate the probability of not A and B, so the intersection of not A and B, which would be, no pun intended, so not A intersection B would be this number here. All right, I'm just going to try to, yep. So if I want to find that number from a probability table, well, really what I'm doing is the 1/8 plus this probability should equal 1/3, right? Because that should give me the sum of the probabilities that adds up to the probability of B. And so therefore I can say probability of not A intersection B equals the probability of B, write it properly, the probability of B minus the probability of A and B, which from this diagram is really clear that it's 1/3 minus 1/8. Right, now this is an exam 1 question I should have mentioned, so no calculators to help us out here, but we should know that when we're subtracting fractions we need common denominators, so we can put both of these over 24. So we get 8 on 24 minus 3 on 24, which equals 5 over 24, and that's our final answer. Okay, second part of the question says to calculate the probability of A dash intersection B, so same probability, but this time when A and B are mutually exclusive events. Now remember that mutually exclusive means they can't both occur, and that means that the probability of A intersection B is equal to 0. Right, now if you go back up to this table, and you'd be welcome to draw it again, but you might not need to. If we were to change this probability from 1/8 to 0, well, then that would mean that this number here, by the same method we just used, would actually have to equal 1/3, because 0 plus 1/3 would have to equal the probability of B. So we could actually say that in this case, the probability of not A intersection B would just equal the probability of B, because they can't both happen together, and that is 1/3. Right, almost a little bit of a trick question there, but not a trick question. We just have to remember that mutually exclusive means the two events can't happen together, which means the probability that they both occur is 0. Okay, pushing through, back to a couple of multiple choice questions here, so calculators back in the game. Question 17 says, the sample space when a fair 12-sided die is rolled is numbers 1 to 12, and each outcome is equally likely. Then it says, for which one of the following pairs of events are the events independent? Right, now that's a pretty wordy, kind of complex question, but the word that stands out to me is independent. Right, remember that we have independent events if the probability of A and B both occurring is equal to the probability of A times the probability of B. Right, that's our independent events formula. And really what's happening in this question is we have to check with all these options which one would give you, or which one would make this formula hold, right? Now, the strategy that I would probably apply first is to start looking at, in each set of events, which numbers are common, right? Because if you want both events to occur, we need to get a number that's in both sets. For example, let's test option A. This is actually one of those questions where really the only way to answer it is to test every option. Okay, so if we were checking the first option here, if I'm looking for the numbers that are in both sets, oh, I've got black ink stuck to my highlighter, sorry about that. I've got the number 1 in both sets, and the number 7 in both sets, right? So that means that if I've got these two events, there's 2 chances out of the 12 numbers. When I roll this 12-sided die, there's 2 different ways that I can get the probability of, that I can get A and B both occurring. 2 chances out of 12. So for option A, right, the probability of A and B both occurring is 2 out of 12, right, which is 1/6. For option A, if I just look at the individual probabilities, well, event A, the first event, has 1, 2, 3, 4, 5, 6 ways out of 12 of occurring. And event B, 1, 2, 3, 4 out of 12, right? Because for event B to occur, there's 4 chances out of 12 that that will actually happen. Now, that's really a half times 1/3, right? Which is equal to 1/6. And of course, what we worked out here, the probability of A and B both occurring, excuse me, 2 out of 12, well, that's 1/6 as well. So what we've actually shown is that with this first option here, the probability of both events occurring is 1/6, but their individual probabilities multiplied together is also 1/6. And that kind of ticks off our independence formula, which means that option A is actually our correct option. If you were to have checked any of the others, we wouldn't get the same result for both of those calculations, right? And if you wanted to just kind of understand what that means a little bit better, let's just pick, say we were testing option E. Option E, when I look at the elements that are common to both sets, I've only got the number 2, right? Which means that the probability of A and B both occurring would be 1 out of 12. But when I multiply the individual probabilities, I've got 1, 2, 3, 4, 5, 6 out of 12. And the second one, I've got 1, 2, 3 out of 12. Right? And so what we'd be needing to happen is that 1/12 is equal to 6/12 times 3/12, but that's really a half times a quarter, and a half times a quarter is only 1/8. So that would be untrue. Right? So this is a sort of question, like I said, where you've got to test each option and see which one actually satisfies the independence formula. And we're a little bit lucky in this case because it was the first option, so we didn't need to keep checking any others. All right, and question 21. And you can usually tell by the number on a multiple choice question that the higher it is, the tougher it's going to be. Nowadays, exams only have 20 multiple choice questions. They used to have 22. So anything that's like up in the high teens or the 20s is going to be a pretty tough question most of the time. Okay, this one says, for 2 events P and Q, the probability of P and Q both occurring is equal to the probability of Q occurring but not P. P and Q will be independent events exactly when. All right, so this kind of combines a little bit the strategy that we use for question 6, because we've just got information about 2 events and some probabilities, and question 17, where we've had to use the independent events formula, because independence, again, is mentioned in this question. And so we could start by thinking, all right, well, for independent events, I would need the probability of P and Q to equal the probability of P times the probability of Q. Now the question's a bit squished together here, so I'm just going to do this, make it clear which working is for which question. All right, so that's something that we know needs to occur for this question to work out. But again, with just information about P and Q, I might be inclined to use either a probability table or a Venn diagram. Just to mix it up, I'm going to use a Venn diagram this time. All right, with overlapping circles, this can be event P, this can be event Q. And what the questions told me at the beginning is that the probability of P and Q both occurring is the same as the probability of not P and Q. Now, it doesn't tell us what that probability is, so I'm just going to call it, call it whatever you want. I'm going to call it X. So what I'm going to write in here is that the probability of P and Q both occurring is X, which is the same as the probability of Q occurring without P. All right, so I'm just going to put that information in as X. Now, if we want independent events, we would need the probability of P and Q to equal the probability of P times the probability of Q. Now, from this Venn diagram, I actually have a bit of that information in terms of X, right? The probability of P and Q is just X in this diagram. I don't have all the information about the probability of P, so I'm just going to write this as PRP still. But the probability of Q from this diagram would just be X plus X, right? It's all the probabilities that are inside the Q circle. And of course, well, x plus x is really just 2x. And so what this is giving me is that the probability of, that x is equal to the probability of P times 2x. And if I were to divide both sides by 2x, I would get the probability of P equals x over 2x, which of course is just a half. So from the information we had and applying it in a Venn diagram, we can actually see that what has to happen is for the events to be independent, the probability of P needs to equal 1/2, and that is what option E says. All right, now that's a tricky question, but again, you can see that starting off with a Venn diagram, or we could have used a probability table, is a useful strategy when you just kind of got this information about two events and some things associated with their probabilities, particularly the intersections. Right, like I said, Venn diagram helpful for question 21. We tried the probability table in that question 6, and both of those were helpful in that type of question. So hopefully you're going to find as you work through these sorts of exam questions more and more, you see the common types of questions coming up over and over again, and you learn a few different strategies that you can apply in order to solve them. As always, get in touch with your teachers if you want to ask any questions about that sort of stuff, but it's bye for now, and I'll see you in the next video.